Okay, I start now. And the presentation is visible to you.
Yes, sir.
Okay, thank you. So, in the previous class, we were discussing about the quantum free electron theory proposed by Sommerfeld. And the main assumptions of this theory were more or less similar to that proposed by Drude. And these are as follows. The electrons which are traveling inside the metal, they are considered as free electrons. By this, I mean that the electron does not interact with other electrons, and the electron also does not interact with the positive ion cores. So, but in the case of the Sommerfeld theory, the electrons are treated as fermions, and their behavior is governed by Fermi-Dirac statistics and the Pauli exclusion principle. So then we uh, took the help of quantum mechanics in order to calculate the energy associated with free electron, and we, in place of the normal boundary condition, we applied the periodic boundary condition. And when we apply the periodic boundary condition, it will give us a solution of a traveling wave, and only a traveling wave can carry energy and momentum. This is the requirement in case of metal. And we calculated what is the energy of free electron that is related with its wave vector as Ek is equal to h cross square k square by 2m. So this is the plot of this Ek diagram we can see here. And at T is equal to 0 Kelvin, all the states, all the K states will be filled up to the Fermi level, and states above Fermi level at T is equal to 0 Kelvin will remain empty. So this is the cube we considered, and if we join the any face of the cube with its opposite face, then we can form we can apply the periodic boundary conditions. And when we apply the periodic boundary conditions, we get this type of wave function for the electron. And then we generated the K space. This is the K space in 2 dimension, and we can see that the periodic boundary condition will ensure that Kx, Ky, and Kz have discrete values, or we can say they are quantized because they have nx, ny, and nz in their in their expressions. So we did, and this is the K space in 3 dimension we can have, and the volume associated with each key point in 3 dimension is 2 pi cube divided by the volume of the cube. We calculated, we define the density of states, number of energy states lying in energy interval dE per unit volume. And for 3 dimension, we calculated that density of state varies as under root of E. So this is how the density of state varies with E. This equation represents the graph of a parabola. So we are going to get the graph of a parabola. And we, based on our discussion, we calculated that at T is equal to 0 Kelvin, we can have a Fermi sphere, and all the states up to Fermi sphere will be filled or will be occupied by the electrons, and these electrons will be accommodated as per the Pauli exclusion principle. And all the K states above the Fermi level will remain empty. So we calculated the Fermi Fermi radius of this sphere, that is known as Fermi wave vector, and it has relation with the electron density. So the relation is n is equal to kf cube divided by 3 pi square. And once we know the relation between the Fermi wave vector and the electron density, we can calculate other important parameters. For example, what is the Fermi energy? So that would be equal to h cross square kf square divided by 2m. And for metals, the Fermi energy varies from 1 to 15 electron volt. So similarly, Fermi temperature, that is related with Fermi energy as follows: EF by kb. So Fermi temperature is of the order of 10 to the power 4 to 10 to the power 5 Kelvin. But we can see that this is much higher temperature in comparison to the melting point of the metals, but it is a theoretical temperature. So Fermi momentum, we calculated the momentum associated with the electrons which lie at the Fermi surface. So that momentum is known as the Fermi momentum. It is equal to h cross kf, and Fermi velocity Vf is equal to h cross kf divided by m. And we calculated the Fermi velocity from this relation could come out to be 10 to the power 8 centimeter per second or 10 to the power 8 meter per second. And then we compared it with the classical velocity calculated by Drude, and we can see that Fermi velocity is one order of magnitude higher than that calculated by Fermi. And these are the some numbers for different metals, namely the electron density, the Fermi wave vector, and Fermi velocity, and the Fermi energy. And this is the picture. Last time I could not show it, but now I am showing it. So at T is equal to 0 Kelvin, all the states up to Fermi energy. So the highest field level will represent the Fermi energy. All the states up to Fermi energy are occupied, and these are filled as per the Pauli exclusion principle. Each state can have 2 electrons of opposite spins. And when the temperature is raised, only these electrons which lie very close to the Fermi level, they will be excited, and these electrons which lie deep in this well, they will not be excited because the states above them are already filled. We also calculated the 0-point energy, or the energy average energy associated with the electron gas at T is equal to 0 Kelvin, and it is 3 by 5 epsilon F. So we discussed about the Fermi-Dirac statistics, and yesterday you explained how to derive this probability function that denotes the probability of finding probability of occupation of any state at energy level E, that is equal to 1 over 1 plus exponential e to the power minus mu upon kBt, where mu is the chemical potential, and at normal temperatures it can be assumed to be equal to the Fermi energy. And this is when we plot Fe as a function of energy. So at T is equal to 0 Kelvin, it is a step function because all the states up to the Fermi level are occupied and all states above it are empty. And when we raise the temperature of the metal, so the states which are near the Fermi level, so they will start becoming empty, and states above Fermi level, they will start being occupied by the electrons. If we multiply the density of states with the probability function, we are going to get the electron density. So this is how we calculate the electron density. And this is the curve for the density of states. And we have a step function for the Fermi-Dirac distribution. So if we multiply the two at T is equal to 0 Kelvin, we are going to get a curve like this that will truncate at Fermi level. And if we are working at higher temperature, then this curve is going to behave or going to go like this at T greater than 0 Kelvin. So here we can see that when we raise the temperature of the metal, then the electrons which are very close to the Fermi level, only these electrons would be excited and they will occupy the state higher than the Fermi level. So only these states are important, or only the electrons lying very close to the Fermi level are important. Today we are going to see the importance of this portion of the graph. So our aim of today's lecture is we will calculate the specific heat associated with the electron gas. And we have seen that Drude calculated it it was 100 times higher as experimentally in comparison to the experimentally observed value. So we define specific heat at constant CV, and it is defined as per unit volume, or the like specific heat associated with every electron. So it is the U is the total internal energy of the electron gas. If we differentiate it with respect to temperature, so we want to know if we raise the temperature of the metal by amount delta T, then how much is the change in internal energy, and their ratio will define the specific heat of the system. If we divide it with volume, then it will give the specific heat per electron. So that V can be absorbed inside this. U over V will give the in energy associated with each electron. So this is how the specific heat per electron is defined. Del small u divided by del T at constant volume. So classically, we know that classically the electrons are treated as behaving like gas molecules. So they have 3/2 kBt energy associated with them. And if N is the electron density, so total U would be total U per unit volume would be 3/2 N kBt. And if we calculate CV, we need to differentiate U with respect to T, we will get 3/2 N kb. And in the previous classes, we have seen that this is 100 times greater than what is experimentally observed. So now we can compare the Drude electron gas and the Sommerfeld electron gas. So in the classical gas, if we increase the temperature, all the electrons gain an energy approximately equal to kb times T. However, in case of Fermi gas or a Sommerfeld quantum electron gas, when we increase the temperature of the metal by an amount of T, only those electrons in states within energy range kBt of the Fermi level, only these electrons will gain this much amount of energy kBt. And this is what is shown here. We have the Fermi-Dirac distribution function plotted as a function of energy. And when we raise the temperature of the metal by amount T, so only those electrons which lie in the kBt region of the Fermi energy, they will be excited. They will absorb this energy and nothing will happen to these lower lying electrons. So what is the fraction of these electrons which are very close to the Fermi level? We know that total number of electrons is denoted by capital N. So the fraction of the electrons which lie very close to the Fermi level, and only these electrons are going to absorb the energy. So their number would be related to the total number as follows: N times kBt divided by epsilon F. And when we are raising the temperature of the metal, only this fraction of the electrons is going to absorb that energy, and that is equal to kBt. So the total electronic thermal energy would be the fraction of the electron and how much energy they are going to absorb. So we are going to get this expression, and if we divide it with volume and differentiate it with respect to temperature, we are going to get electronic specific heat, or the specific heat per electron. So that would come out to be N kb into kBt divided by epsilon F. So here this epsilon over kb is of the order of 10 to the power 4 to 10 to the power 5. Basically, it is inverse kb over EF is inverse of Fermi temperature. So we can also write it as T over TF, and KBT at room temperature divided by the Fermi energy is of the order of 0.01. So with this expression, we are going to get the specific heat associated with each electron that is 100 times smaller than what is predicted classically or by the Drude model. So we would see that Sommerfeld very correctly explained the contribution of electrons to the specific heat. So this is an estimate, or this is qualitative expression which we have derived. The electronic specific heat expression, we have derived it qualitatively. Now we would like to understand it quantitatively, how we can derive it. So now our aim is to derive an expression for the electronic specific heat quantitatively. And the derivation of electron specific heat, or the electron heat capacity, is applicable to the regime when a Fermi gas does not behave like a classical gas. That is, when the temperature is much smaller than the Fermi temperature, or the KBT energy is much smaller than the Fermi energy. And remember, the Fermi energy is of the order of 1 to 15 electron volt for metals, and KBT around room temperature is 25 milli electron volt. So we are working in a regime where KBT is much smaller than the Fermi energy. Now, in order to calculate the specific heat associated with electron gas, so we need to calculate what is the change in the internal energy if we raise the temperature of the metal from 0 to a temperature T. So that change in internal energy when electrons are heated up to a temperature T from 0 Kelvin is given by delta E, that is equal to E at temperature T minus E at temperature T is equal to 0 Kelvin. Now we can write it, what is E at temperature T. So we know that if we multiply the density of states with the Fermi-Dirac distribution function, we are going to get the number of electrons per unit volume. And if we multiply these electrons with energy, so we are going to get the total energy associated with n electrons at temperature T. So this is, we have written integration from 0 to infinity E times GE f of E dE minus. Now we have to calculate what is the energy at T is equal to 0 Kelvin. So, sorry, we know that this Fermi-Dirac distribution function f of E at T is equal to 0 Kelvin would be equal to 1. This means all the states up to Fermi energy are occupied, and all states above Fermi level are empty. Therefore, in this expression, f of E would be 1, and we will have the integration only from 0 to EF, because all the states at T is equal to 0 Kelvin above Fermi level are empty. So we will have 0 to EF E GE times DE. And we also know the expression for density of states, that is 1 over, so we need to put the density of state expression here, 1 over 2 pi square times 2m upon h cross square to the whole power 3 by 2 under root E. So in this expression, we have two integral terms which share the total energy. So I have already explained how we get it. We multiply the energy by how many electrons have that energy, and how many electrons we calculate. We multiply density of states by the Fermi-Dirac distribution function, and then we calculate the number of electrons, and if we multiply it with energy, we will get the energy at particular temperature T. So we know that total number of electrons in the metal is going to remain fixed. They are not going to change whether we are working at T is equal to 0 Kelvin or we are working at higher temperature. The total number of electron is not going to change. So we can have the total number of electrons at finite temperature would be equal to total number of electrons at T is equal to 0 Kelvin. So total number of electrons at finite temperature is given by density of states multiplied by Fermi-Dirac distribution function, and we can integrate it from 0 to infinity. This is the first integral, is the number of electrons at finite temperature T. And this is going to be equal to the number of electrons at T is equal to 0 Kelvin. Here f of E again would be equal to 1. We will have only GED. And the limits of integration would be from 0 to EF. So the rightmost integral is the total number of electrons. This integral is the total number of electrons at T is equal to 0 Kelvin. And the other integral is the total number of electrons at finite temperature. And since the number of electrons in the metal will remain same, so therefore these two integrals must be equal. Now if we multiply both sides by EF, so this is a constant, it can be multiplied and it can be kept inside the integral. So we are going to get this expression. Integral 0 to infinity EF GE f of E dE would be equal to integral 0 to EF GE dE. Now we can split this integral on the left hand side. It has limit from 0 to infinity. We can break it into two parts. One integral has limit from 0 to EF, and other integral will have limit from EF to infinity. So after breaking, we write it 0 to integral 0 to EF GE f of E dE plus integral EF to infinity EF GE f of E dE, and that is equal to integral 0 to EF GE dE. So now we can see that we have this integral and this integral on the other side, they have the same limits. So we can bring this term on this side and we will get minus sign. So 0 to integral 0 to EF G of E times f of E minus 1 into dE plus integral EF to infinity EF GE f of E dE is equal to 0. So after reshuffling the terms, we will get this expression. So we can take this first term on the right hand side and this will give us minus sign. So we will have minus of integral 0 to EF GE f of E minus 1 into dE would be equal to this expression. So I have kept it inside the box because we are going to use it later. Now we write the expression for delta E, that is equal to E at temperature T minus E at T is equal to 0 Kelvin. So this is the expression for delta E. Integral 0 to infinity E G of E f of E dE minus integral 0 to EF E GE dE. Again, we can split this integral. This has limits from 0 to infinity. We can break again it into two parts. So one integral is from 0 to EF and the other integral is from EF to infinity. So now we will have three terms on the right hand side. If we add and subtract simultaneously this term from this, so then the last equation will become, now it is going to have 5 terms because we are simultaneously subtracting and adding this term. So we have 1, 2, 3, 4, 5. This is addition and subtraction of this term. So now we will have 5 terms. So now here we have this term, or for example, this term, this is positive sign, and we have proved this is equal to this. So in place of this fourth term, we can write this term. So after writing, delta E would become 0 integral 0 to EF E g of E f of E dE plus integral EF to infinity E g of E f of E dE minus 0 to EF E g of E dE minus integral 0 to EF GE f of E minus 1 dE minus integral EF to infinity EF GF of GE f of E dE. Now you see there are three terms that integral terms that have limits from 0 to infinity. One, and this is second, and this is third. We can club them together, and the two terms have integral limits for EF from EF to infinity, and we can club these terms together. So this is just I have rewritten the expression, and we arrange all the terms together. First, you can see that here the terms which have limit EF to infinity, they have been clubbed together, and then we can club this term and this term. So this will give this, and after a little bit of mathematics, we are going to get, so all the terms have been clubbed together, we are going to get two terms. Now we are going to get the expression delta E is equal to integral EF to infinity E minus EF GE f of E dE plus integral 0 to EF E minus EF GE f of E minus 1 into dE. Again we can see that so we can write it. It is f of E minus 1. If we take minus sign outside, it can be written as 1 minus f of E. So this is the expression for change in the internal energy of electron gas when its temperature is changed from T is equal to 0 Kelvin to at a temperature T. The first integral, this one on the right hand side, describes the energy needed to take electrons from the Fermi level to the higher energy level. And the second integral describes the energy needed to excite electrons from lower energy levels up to the Fermi level. Now we have found the expression for delta E. We can calculate the specific heat associated with electrons. The specific heat is found by differentiating delta E with respect to temperature, and the only term in the integrals which have temperature dependence are f of E. This Fermi energy is constant, density of state is constant, only the temperature dependency is given by f of E. So we write C electronic is equal to del delta E divided by del T, that is equal to integral EF to infinity E minus EF GE, and we differentiate f of E, that is a function of energy and temperature, into dE plus integral 0 to EF E minus EF G of E, and first derivative of f E with respect to temperature times dE. We can see that the expression inside the integral in the two terms is equal, and it is like we have separated the limits. So we can add the limits, and now the total expression would become from 0 to infinity. This is from 0 to EF, and the first term is from EF to infinity. We can mix the limits, so the total expression would become integral 0 to infinity E minus EF G of E del f of E and T divided by del T into D. That is the expression for electronic specific heat that we have calculated quantitatively. Now we need to again understand it, and we need to further solve it in order to have some idea about so that we can simplify it and can calculate the electronic contribution to the specific heat. So we have mixed the two integrals back together. After the temperature derivative produce the same integrand. Here you have the integrand is same. So we have mixed the two integrals. And the temperature derivative of f of t. So if you recall, the Fermi-Dirac distribution f of E, when it is plotted at t is equal to 0 Kelvin, it is a step function. And one day I discussed that the first derivative of Fermi-Dirac distribution function is a delta function that has value only at Fermi level, and beyond either side of the Fermi level, it goes to 0. So the first derivative of a step function like Fermi-Dirac distribution function is a Dirac delta function, which has finite value only close to the Fermi level, and beyond that it goes to 0. So the derivative of this Fermi-Dirac distribution function is peaked close to Fermi energy. Therefore, only the states which lie at the Fermi level, only the density of those states are important. Therefore, in this expression, we can replace G of E by G at EF. And we know that G at EF is a constant, and it can be taken out from the integral. So this is another way of saying that only electrons which lie close to the Fermi level, only these electrons matter. Therefore, we have this expression changed to CEL approximately equal to G at EF integral 0 to infinity E minus EF and first derivative of Fermi-Dirac distribution function with respect to temperature times dE. Again, we are writing the same expression. So now we need to take the temperature derivative of this Fermi-Dirac distribution function with respect to temperature. We know that f of E and T is equal to 1 upon exponential 1 upon 1 plus exponential E minus mu upon kBT. And for all working temperatures, we can replace chemical potential by Fermi energy, because kBT upon EF or T upon TF is much, much smaller, 0.01 at room temperature. Therefore, at all working temperatures, you would see in some books in place of mu, it is written as EF. So then we differentiate it with respect to temperature. We are going to get this expression. You can see it by yourself. This is like 1 upon x. So it is going to give x square. We will have minus sign, and minus minus would become plus. When we differentiate it, you can check it by yourself. So it would be E minus EF divided by kBT square times e to the power E minus EF divided by kBT upon e to the power E minus EF divided by kBT plus 1 to the whole square. Now we assume that E minus EF upon kBT is equal to x, and then we calculate how the limits are going to change, and then we will get this expression CEL would be equal to G at EF times kB square T, and the now limits are going to change from minus EF divided by kBT to infinity, and we will have inside the with the integrand would be x square e to the power x divided by e to the power x plus 1 to the whole square dx. Now we are working in a temperature range where kBT is much, much smaller than Fermi energy. As I told you, kBT value at room temperature is 25 to 30 milli electron volt, and Fermi energy is of the order of 1 to 15 electron volt. Therefore, KBT is much, much smaller than EF, and therefore EF upon KBT would be very high, and this is minus. So we can replace the lower limit by minus infinity. So now the integrand in this integral can be written as G at EF kb square t integral from minus infinity to plus infinity x square e to the power x divided by e to the power x plus 1 to the whole square dx. And this is a definite integral, and its value we know. So its value is equal to pi square by 3. It is a definite integral. So this expression would become GEF kb square t pi square by 3, and all the terms G at EF it is constant, kb is constant, pi is constant, 3 is also constant, everything is a constant, and that can be written equal to gamma. So we can write CEL is equal to gamma t, where gamma is equal to G at EF times kb square pi square by 3. And we know that this is density of state at Fermi level. It is related with the Fermi energy as follows: 3n divided by 2 EF, and EF is kBT TF, kBT TF. Here, please understand it is TF. So it is 3n divided by 2 kBT. So now we have in the denominator EF expression for Fermi energy, that is equal to h cross square kf square by 2m. So this gamma constant is related with the mass of the electron, because EF is in the denominator. So m here will come in the numerator. Gamma is proportional to the mass. So this constant gamma is known as the Sommerfeld constant, and this mass is not just the mass of the free electron, but we would see that it is the effective mass of the electron. It is the effective mass of the electron. Just a minute. So we can have this Sommerfeld constant that is proportional to the effective mass of the electron. And this concept of effective mass is very, very important. We will see shortly how it is important. So we can write the expression for electronic specific heat equal to pi square by 2 when we substitute 3 by 2 n divided by 2 EF, and in place of EF we write kBT into TF. So the expression for the electronic specific heat would come out to be pi square by 2 n kb into T over TF. So here we can see that this is the same expression more or less as we derived qualitatively. And here we see the electronic specific heat is proportional to temperature, to the first power of temperature. So electronic specific heat increases linearly with temperature. This is the quantitatively derivation of the electronic specific heat. Now, a comparison of this result with that of Drude proves that while for an ideal classical gas, electronic specific heat is 3 by 2 N kb, whereas we have just derived this relation CEL is equal to pi square by 2 N kb times kBt divided by epsilon F as per the Sommerfeld quantum free electron theory. This is proportional to T, whereas you see it is temperature independent. So it is going to, as per Drude, the specific heat of electron is going to remain constant at all temperature. However, experimentally, it is observed that electronic specific heat varies linearly with temperature, and this is what we have proved using the Sommerfeld quantum free electron theory. And this is 10 to the power minus 2 order smaller than this at room temperature. And this is what is observed experimentally. So because the electronic contribution to the specific heat at room temperature is very, very small, and this explains the absence of any observable contribution of electronic degrees of freedom to the specific heat of a metal at room temperature. This electronic specific heat dominates dominates at very, very low temperature, close to 0 Kelvin. Its contribution can be seen up to 4 Kelvin only, from 0 to 4 Kelvin. Above that temperature, the ionic specific heat starts dominating. The linear, so if we want to observe the electronic specific heat, then we need to suppress all other degrees of freedom which are contributing to the total specific heat. For example, the ionic degrees of freedom that dominate the specific heat at high temperatures, but well below room temperature, their contribution falls off as T cube. So this is famous Debye T cube law for specific heat of atoms or ions that we will study in the next class. And so well below room temperature, the contribution of ions to the total specific heat falls off as T cube faster than electronic contribution proportional to T. The latter can thus be seen at a few degrees Kelvin, that is closer to 0 Kelvin. Now we can write the total expression for electronic specific heat, total expression for specific heat, that will have one term from the electrons and the other terms from the phonons or the ions or the lattice vibrations, whatever you call it. So the total specific heat is the specific heat due to phonons or ions, and plus the specific heat contributed by the electrons. And we see the first expression, it has T cube expression. So this is the Debye expression for the specific heat of ions or atoms. And this is the second expression that we have just derived. The ionic contribution to the specific heat is proportional to T cube, whereas the electronic contribution to the specific heat is proportional to T. Now it is a customary to plot C by T. So for example, if we divide it by T, here we will have T square, and here we will have only the constant. Everything is constant for a particular metal. TF is also constant. So we are going to get this expression C by T is equal to gamma plus A T square. So this is what is plotted for metal. And if if we plot C by T as a function of T square, we are going to get a straight line. And the A constant will give the slope of the straight line, and the intercept on the y-axis will give the value of y, because it is y is equal to C plus mx. So m is slope that is given by A, and intercept on the y-axis is given by this gamma. So this is observed in most of the metals. So for example, we are showing here the example for electronic specific heat for potassium, and you see the graph between C by T versus T square, it varies linearly. and the intercept on the y-axis, it is going to give the value of the Sommerfeld constant, and its slope is going to give the value of this A. And what is A? We can see from here. So the actual picture of electrical conduction is thus quite different from the classical free electron theory, in which we assumed that the thermal current is carried equally by all electrons. So according to classical theory or the Drude theory, when we raise the temperature of the metal, then all the electrons are assumed to absorb this energy. However, according to the quantum theory, only those electrons which lie close to the Fermi level, only these electrons contribute to the specific heat or the electrical conduction or the thermoelectric power. So this is this much. So if we substitute tau f is equal to LF upon VF. Tau f is relaxation time at Fermi level. It is the relaxation time associated with electrons that lie at the Fermi level. LF is their mean collision distance, and VF is their Fermi velocity. So in the expression, if we write for the conductivity expression now according to the Sommerfeld theory, it would give us Ne squared tau f upon m, and that is equal to Ne square upon m into Lf upon Vf. And classically also we got this expression Ne squared tau upon m. So both approaches lead to the same result, but this Sommerfeld quantum free electron theory is more accurate. This can be seen from the fact that only the collision time for electrons at the Fermi surface, that is tau f, appears in this expression. The only quantity on the right hand side which depends upon temperature is this Lf. Only this quantity depends upon temperature, and Lf is Lf varies as 1 upon T. So since Lf varies as 1 upon T, so sigma is going to vary as 1 upon T, or rho is going to vary as proportional to temperature. And this is what is observed experimentally. However, according to the Drude model, conductivity varies as 1 upon under root T. But here, according to Sommerfeld, we have proved that electrical conductivity is proportional to 1 upon T, or the electrical resistivity is proportional to the temperature. Now we are going to discuss more about this Sommerfeld constant. The experimental value of gamma is very important because it is a customary way of extracting the electron effective mass from the experimentally observed value of gamma. In real metals, the electrons do not always behave as if they have m equal to mt. Just a minute. Yes. So in real metals, the electron will not always behave as free electrons, as we are assuming it theoretically. M will not always be equal to M of E. Sometimes the electrons in metal behave as if they are heavier particles. Heavier particles means their mass is, their effective mass is much heavier than the mass of free electron. And so in that case, we need to consider the effective mass of the electron, and that would be defined as m star. Somewhere you can see that it is defined as m of E star, with a star. In some compounds called heavy fermions, these are known as heavy fermion compounds, electrons can behave as if they have effective mass that is 1,000 times the mass of free electron. An enhanced effective mass can be caused by interaction of electron with other electrons, with interaction of electrons with the periodic potential or the positive ion cores. And we know that in Sommerfeld expression, we have ignored the interaction of electron with other electrons and its interaction with other positive ion cores. But in practice, or actually or experimentally, the electron inside the metals will interact with other electrons and they will also interact with positive ion cores. Therefore, in such metals, the electrons' effective mass could be much higher than the mass of a free electron. So when heat capacity is used to extract effective mass, this is called the thermal mass, M, and it is denoted by M thermal. That is the experimental observation, and that is related with the effective mass, that is related with the mass of the electron as M thermal divided by Me is equal to gamma, that is observed experimentally from this graph, and to the ratio gamma for free electron. So gamma is related to the electron mass because mass is inversely proportional to the Fermi energy, as we have already seen it. Somewhere we saw it. Here we saw it. Gamma is inversely proportional to the Fermi energy, which is inversely proportional to the mass. So mass of the electron is proportional to gamma. Now, we have shown the measured value of gamma and the proposed or the free electron gamma for certain metals. For example, you can see in case of lithium or sodium, the free electron mass is 1.8, and with this unit, so this gamma is this much, 1.8 into 10 to the power minus 4 calorie per mole into Kelvin square. Experimentally observed value is 4.2. Therefore, effective mass to the mass of free electron ratio is 2.3. So for normal metals, it is more or less similar. So for example, silver 1.5, experimental and theoretical value both are same. We are going to get 1. But for certain metals, you see it deviates from very much from 1. So for example, you see niobium, the ratio is 12. For manganese, it is 27. For iron, it is 8. So for certain metals like manganese, iron, niobium, and certain other metals, this ratio is very much different from unity. Therefore, in these metals, the electron will behave as if they are much, much heavier in comparison to the free electron. The departure from the unity involves 3 separate interactions. First is the interaction of the electron gas with the periodic potential that is formed by the positive ion cores. The effective mass of an electron in this potential is said to be the band effective mass. The interaction of these free electrons with phonons or lattice vibrations. An electron tends to polarize or distort the lattice in its neighborhood so that the moving electron tries to drag nearby ions along, thereby increasing the effective mass of the electron. The third interaction is the interaction of the conduction electron with themselves. That is the interaction of the electron with other electrons. A moving electron causes an inertial reaction in the surrounding electron gas, thereby increasing the effective mass of the electron. So these are the three interactions that will give rise to the phenomenon of effective mass. That is, the electrons will behave as if they were the mass, or they were the particles of heavier mass in comparison to the free electrons. So I told you about the heavy fermion compounds. So for example, several metallic compounds have been discovered that have enormous value, 2 or 3 orders of magnitude higher than the usual of the electronic heat capacity constant, or the Sommerfeld constant. The heavy fermion compounds include uranium, beryllium 13, UBE13, CeAl3, and CeCu2Si2. It has been suggested that F electrons in these compounds, F electrons means they will have either the 4f orbital or the 5f orbital. So accordingly, the electrons present in 4f and 5f orbitals, these electrons may have inertial mass as high as 10 to the power 3 or 1000 times mass of a free electron, because of weak overlap of wave function of f electrons on neighboring ions. So this is what we have discussed quantitatively about the electronic specific heat contribution, and we have seen how beautifully Sommerfeld theory explained the electronic contribution to the specific heat. And please remember, I repeat it again, that the electronic contribution to the specific heat is dominant only at very, very low temperature, closer to 0 Kelvin. At high temperature, it is the ions whose contribution will dominate. So now we are going to discuss about the electrical conductivity and Ohm's law as per the Sommerfeld free electron theory. So we know that the momentum of a free electron is related to its wave vector according to quantum mechanics as follows. mv, that is the momentum of the mass that is moving with velocity v, that is equal to h cross k, where k is the wave vector of the electron. When we apply electric field, external perturbation in the form of electric field to this electron gas, so this electron will move as per the Newton's second law of motion. So the electric field will give rise to change in momentum, and the rate of change of momentum m dv over dt is equal to h cross k dk over dt, that is equal to the force experienced by the electron on the application of electric field E. So that would be equal to minus E times capital E. In the absence of collisions, the Fermi sphere moves in k space, because this electric field, this force of electric field is going to accelerate the electron gas. If there is no collision present, then this Fermi sphere will move with a uniform rate by a constant applied field. If the applied field is constant, then it will produce a uniform speed, and therefore, if the collisions are not present there, then this Fermi sphere is going to move at a constant speed. But we know that there are collisions of electrons with other electrons that will deaccelerate the motion of the electron. Therefore, we will see what is going to happen. So when we integrate it with respect to 0 to t, so we are going to get k wave vector at time t minus wave vector at t is equal to 0 time is equal to minus e t upon h cross. So this is the Fermi sphere we have plotted in the momentum space, and this is Fermi sphere at time is equal to 0 second. So now, if we don't apply any electric field, we know that we are not going to get any current from the metal. And the explanation is very interesting here. In the absence of electric field, the Fermi sphere is centered at the origin. As we have seen, this is the Fermi sphere that is centered at origin. The various electrons are moving, some at very high speeds and some at lower speeds. So, for example, in the Sommerfeld theory, the electrons which are near the Fermi level, they have the Fermi speed that is equal to 10 to the power 8 centimeter per second or 10 to the power 6 meter per second. But the electrons which are deep in the Fermi sphere, they have smaller velocity. So electrons in the Fermi sphere, they have the different speeds or velocity, and these electrons carry individual currents because they are moving here and there. But the total current of the system is zero, because if you consider the electron that is present here, it is moving in this direction with the speed v, and corresponding to this wave number, we have another electron that is present here at the same k number, but with the minus k value. Therefore, this electron is moving in this direction with the speed v, and the electron present here with the same wave number, it is moving in the opposite direction with the same speed v. Therefore, one electron is moving in this direction, the other electron is moving in the opposite direction. They have equal but opposite speeds. The sum of their and each electron is carrying current. Therefore, sum of the two currents is zero. Thus, the total current vanishes due to pairwise cancellation of the electron currents in the absence of electric field. Now we would like to see what is going to happen if we apply electric field. So we have seen that the force of electric field on the electron would be minus small e times capital E, and this force is applied when the Fermi sphere is centered at origin, and so this is considered at time t is equal to 0. An electron gas that fills the Fermi sphere centered at the origin of k space, or the momentum space, or the velocity space, whatever you call it, then at time t, so the electric field is applied in this direction. This electron gas is moving due to this force of applied electric field. This electron gas is going to move in this direction. So you see, this circle represents the movement of electron due to this applied electric field, and the center has shifted. Now this is the center of this sphere, and earlier it was the center. So the center of this Fermi sphere has shifted in the k space by amount delta k. And this delta k can be equal, we have already seen, delta k is equal to, we can very well calculate it, minus EET divided by m. We notice that the Fermi sphere is displaced as a whole because every electron is displaced by an amount delta k. But we will see that if we consider this region, look at the cursor. If we consider at this region, for every electron that is moving in this direction, there is another electron that is also moving. So the contribution of these electrons would be equal to 0. Here you have minus k and here you have plus k. So the contribution of these electrons which lie deep inside this Fermi sphere, their contribution will be 0. But however, you see only this region, the shaded region, these electrons do not have any counterpart on the positive side, because those electrons which are already here, they have shifted to this side. Therefore, only these electrons will give rise to current, and therefore, with the application of electric field, we are going to get current in the metal because these electrons remain uncompensated. The electric field is in the positive x direction, is each electron acquires a drift velocity that is equal to, so momentum mv, that is equal to h into delta k. So v would be equal to h cross delta k divided by m, and that is equal to minus e, capital E, tau divided by m. So this is what we have written the expression for delta k. So thus the whole Fermi sphere is displaced to the left as shown in this figure. Although the displacement is very small, and although the great majority of electrons still cancel each other. So in this region, please see the cursor. In this region, the electrons will cancel each other, because for every electron with negative k value, we have electron with positive k value also. Some electrons in the shaded crescent, this shaded crescent in the figure remain uncompensated, and it is these electrons which produce the observed current. So now we would like to introduce the collision term also, because the electrons feel collision with other electrons, and because of the collisions, the displaced Fermi sphere is maintained in a steady state in an electric field. If the collision is not there, the speed of the electron will keep on increasing. So we have already seen this equation. Del P at time t divided by del T is equal to minus P momentum of electron at time t divided by tau plus external force at time t is equal to 0 under this steady state condition, when the collision that is deaccelerating the electron and the applied electric field that is accelerating the electron, when the two forces balances. So we will achieve the steady state. Under steady state, the electron momentum will become constant. It will not change with respect to time. So that will be equal to 0. So from here we get P at time t would be equal to F time tau, and F we know that it is the force due to applied electric field, that would be equal to minus E, capital E, times tau. If the collision time is tau, the displacement of Fermi sphere in the steady state is given by delta k is equal to minus E, capital E, times t divided by m. And we can replace this t with tau. The incremental velocity would be given as momentum is equal to mv h cross delta k. So we can calculate the incremental velocity, that would be equal to minus e tau upon m. This is what we get here. Now we know if we apply electric field, then if there are small n electrons of charge minus e per unit volume. So this is small n represents the electron density. That would be equal to J is equal to minus NeV. We write the expression for V from here. So we will get Ne square E tau upon M. And what is this? Ne square tau upon M? It is conductivity, expression for conductivity. So sigma is equal to Ne square tau upon M, or electrical resistivity that is related to conductivity as 1 over rho. It would be equal to m upon Ne square tau. And you know that because only the electrons which lie close to the Fermi level, they contribute to the electrical conduction. Therefore, we can have T is equal to TF, the collision time of an electron at Fermi surface in this expression. So Sommerfeld was successful in deriving or in explaining the electrical conduction using this quantum free electron theory. This is the same expression that was derived by Drude. Similarly, we can understand about the thermal conductivity of metals. We have already found this expression when we discussed the thermal conductivity as per Drude theory. So kappa was equal to 1 by 3 V squared tau into CV for the thermal conductivity of particles moving with velocity V. and having relaxation time given by tau, and with we specific it is smaller, small v per unit volume. So that is there. The specific heat per unit volume of a Fermi gas, we have already seen this expression, pi square by 2 n kb square T upon EF, or we can write Fermi energy as 1 by 2 mVp square. Fermi energy is the kinetic energy of the electrons which are moving with velocity Vf. So we can write pi square by 2 n kb square times T upon 1 by 2 mVp square, that is equal to pi square n kb square T. So this 2 and 2 would cancel out. We will get T upon mVp square. The thermal conductivity of a Fermi square, now we know CL, we can write here. So we get the expression for thermal conductivity as, or the coefficient of thermal conductivity as pi square by 3 n kb square capital T times tau divided by mVf square. So now the question arises, do the electrons or the phonons or ion carry the greater part of this heat current in a metal? So this is thermal conductivity. So we represent it by thermal current or the heat current. In pure metals, the electronic contribution is dominant at all temperatures. The thermal current is carried by the free electrons. That's why we have the Weidmann-French law that states that good electrical conductors are also good thermal conductors. So in such metals, the electronic contribution is dominant. However, if we have impure metals, there we will have impurity of other metals, and they are going to contribute. In impure metals or in disordered alloys, the electron mean free path is reduced by collisions with impurity. And remember, tau is equal to tau f, that is proportional to LF. So their mean free path is reduced. Therefore, kappa or electron in such impure or disordered alloys would be smaller, and there the phonons contribution to the thermal conductivity will dominate, or it would be comparable with the electronic contribution. So now we understand the importance of Fermi sphere in transport phenomena is clear. Since the current is transported by only those electrons which lie close to the Fermi level or Fermi surface, these phenomena are very sensitive to the properties, shape, etc. of this surface. So far, we have considered the Fermi surface to be the surface of a sphere, but practically it is not the case. And we have seen that all the electrical and thermal properties depend upon this Fermi surface. So if the Fermi surface is going to be different shape, it is not as a Fermi sphere, rather it is having different shape. That is the case practically. So the inner electrons are irrelevant so far as conduction process are concerned. We have seen that only those electrons which lie close to the Fermi level, they will contribute. Therefore, the inner electrons are irrelevant as far as the electrical conduction and thermal conduction are concerned. Now, we have derived the expression for electrical conductivity. We had derived the expression for thermal conductivity. Therefore, we can again define the Weidmann-French law. It states that for metals at not too low temperatures, the ratio of the thermal conductivity to the electrical conductivity is directly proportional to temperature, with the value of constant of proportionality independent of the particular metal. So kappa by sigma, if we write the expression as derived by Sommerfeld theory, we will get this expression pi square by 3 kb divided by E to the whole square times T. So you can see that this ratio is proportional to temperature. So at fixed temperature, it is equal to Kb here is constant, E here is also constant. See, this whole constant is known as the Lorentz number denoted by L. Its value comes out to be 2.72 into 10 to the power minus 13 erg per ESU degree to the whole square, or 2.45 into 10 to the power minus 8 watt ohm per degree square. And this is the experimental Lorentz number for different metals observed at 0 degree centigrade and 100 degree centigrade. So, and it has the multiplication factor 10 to the power 8. Please remember, experimental value is 2.45 into 10 to the power minus 8. So here you see it is 2.31 into 10 to the power minus 8. It is 10 to the power minus 8, not 10 to the power 8. And so it is very close to the what we have observed here. So Sommerfeld quantum free electron theory was successful in explaining the Wiedemann-French law also. Let me see. So I have 2 more slides. So we can discuss the thermopower or thermoelectric power of metals also as per the Sommerfeld free electron theory. And we know that when we discuss about the thermoelectric power, we have this Seebeck effect. If we have a temperature gradient in a long thin bar of metal, and so if we have a temperature gradient, then it is accompanied by an electric field. We know that this is known as the Seebeck effect. If a metal is kept at 2 different temperatures, its 2 ends are kept at 2 different temperatures. Therefore, an electric field is generated or electric voltage is generated that is known as the thermopower, though it is a misnomer. And this is, you see how there is a long thin metal bar. This end is kept at high temperature T, the other end is kept at low temperature. So there is a temperature gradient. So it will give rise to an electric field or electric voltage in this direction, which is related to this temperature gradient as follows. E is equal to Q times del T, where this Q is known as the coefficient of thermopower. And Q is given as minus CV upon 3NE. And as per Drude classical theory, CV was equal to 3 by 2 NKB. If we want to calculate Q, so then it would come out to be minus KB upon 2E. This is incorrect. This is 100 times greater than what is experimentally observed. But Sommerfeld theory provides electronic contribution to the specific heat as given by this formula. Therefore, C Sommerfeld divided by C Drude is of the order of 0.01 at room temperature, and the thermopower calculated from the Drude model and its ratio, the thermopower calculated from the Sommerfeld model and its ratio with the Drude model is also equal to 0.01 at room temperature. And Q would come out to be, as per Sommerfeld theory, this was come out to be this, and this would be equal to 10 to the power minus 6 volt per Kelvin. It would be equal to 10 to the power minus 6 volt per Kelvin, and this is what is observed experimentally. According to Drude, it was of the order 10 to the power minus 400 times greater than what is experimentally observed. So this is all effects we discussed. Using quantum free electron theory proposed by Sommerfeld, but it is, though it is successful in explaining many things, but again it has several drawbacks also. This model suggests that, this model means Sommerfeld quantum free electron model. Other things being equal, electrical conductivity is equal to electron concentration. We have expression for electrical conductivity, N E squared tau upon M. So if other things are equal, sigma is proportional to N. But it is surprising that divalent metals, for example, beryllium, cadmium, or zinc, and even trivalent metals like aluminum or indium are less conductive than monovalent metals like copper, than silver, than gold, despite the fact that former have higher concentration of electrons. Former means this. So as per electron theory, for example, aluminum is contributing 3 electrons to the electron gas. So it should be more conducting than copper. And this is question for you. Why, if aluminum or magnesium is contributing more electrons to the electron gas in comparison to copper, which contributes only 1 electron, but copper is more conducting than aluminum and magnesium? That is question for you to answer in the next class. So that is one problem for this Sommerfeld quantum free electron theory. And next problem is the same problem that could not be explained by this positive Hall coefficients for observed for certain metals like beryllium, zinc, and cadmium. This quantum free electron theory could also not explain why some metals exhibit positive Hall coefficient. In the third failure is in this Sommerfeld quantum free electron theory, we have considered Fermi surface to be of the spherical shape, but it is observed that it is not the case for many metals. Fermi surface is not of spherical shape for many metals. So again, here it is the failure of quantum free electron theory. And as we have seen, this quantum free electron theory does not consider the electron-electron interaction or the electron-ion interaction. And it can also not explain about the heavy fermion compounds in which the electrons behave as if they were having mass that is 1,000 times higher than the effective mass of free electrons. So this is all about the quantum free electron theory. And with this, we conclude first unit of your syllabus. In the next class, we will discuss something. So with this, I conclude my lecture.